The sixth video gives some miscellaneous insights and useful ways of using logarithms and exponentials. So you're reminded that these videos are really focused at perhaps engineering undergraduates just entering university. So far we've looked at definition, properties and algebra of exponentials and logarithms. This video is just going to add a few minor observations which are useful for engineering problem solving. We're going to look at log graph paper, and we're going to look at how you might identify exponentials where they exist in real data. So some background. Just a reminder that a logarithm is defined as the inverse function of an exponential. So in other words, if we had something like y equals e to the x, then the logarithm is defined as x equals log e y. And we've gone through a number of useful properties, things like the product rule, so the log of a product is the sum of the logs, or the log of a quotient is the difference of the logs. And we've got the power law, that log of something to the power is the power times the log of the original number. Now another one, which is perhaps less recognised, but we're going to look at in this video, is this rule here, that if you've got log e of a e to the ax, you can write it as log e capital A plus ax. In other words, it gives you a straight line. So, if we want to identify exponential behaviour within some data, then we find that we can simply take logs. So here's the sort of question. We've got a number of items of data here. You can see 0.86, 0.65, 0.55 and so on. I've plotted them here, and I look at that, and if I do a sort of line, you say, well, it looks to me like there's probably an exponential underlying that data. But how do I decide, is there indeed an exponential? Because the eyes can be deceitful at times. So this is where logs come in. What we're going to do is use this expression here, that log e of a e to the at is log ea plus at. And if I wrote that, for example, as equal to y, you can see clearly that's the equation of a straight line, where this is the intercept, and little a is the gradient. So if I can find a straight line, then I can get the intercept and the gradient by inspection, and therefore I can identify the parameters capital A and little a. So if the function is indeed exponential, so that means if y of t is indeed an exponential function, then when I take the logarithm of y, I will get a straight line. So what we're going to do is take the data of the previous page and plot the log of this data. Now, just as a sort of a summary, if y is less than 0, it's negative, then you need to plot log of the modulus of y. I'm not going to dwell on that level of detail, but you can't do log of a negative number. So here we've done it. We've taken the data from the previous page, and I've essentially just taken the log of that data and plotted it, and that's given me these blue points here. And then you can see it's pretty obvious that they lie on a straight line, because real data is always a little bit noisy. It's not going to be perfect, and so I can fairly easily fit a straight line through that data. And now I've got the straight line, all I need to remember is that the intercept is going to be log of a, and the gradient is going to be a. So from this I can work out capital A and little a. And so just in case you hadn't noticed, if I extend this back, then the intercept is going to be somewhere around here. But I'm going to do this more cleanly on the next page. The key thing here is that once you've plotted the log of the data, you can immediately see that the data is lying on a straight line, and therefore you know that the underlying signal was an exponential. So just to check, find the exponential function y of t underlying the following graph where I've plotted log of y. So first of all, we say, well, what are we doing? We're writing the log of the data, so that's log a e to the at, which we know gives me log e capital A plus at. And so now Log e of a must be the intercept with the vertical axis. Now in this particular case, here's the vertical axis. There's the intercept, and you can see the intercept is 0. So in other words, log e a equals 0 implies that a equals 1. Silly student mistake would be to say, oh, therefore capital A is 0. And of course it's not, it's 1. At is the gradient. Now if I look here, you'll see that I've moved along a distance of 4, and I've moved down a distance of 0.4. Clearly the gradient is negative, so I've got a gradient of minus 0.1. So I put all that together, then what you get is my original function must be log y equals minus t over 10, or y equals e to the minus t over 10. So where you couldn't necessarily get those parameters easily from the original data, by taking log of the data, you've been able to get to the parameters in a straightforward manner. Log graph paper. Now there's two ways of viewing log graph paper. Both are valid, and you can use whichever you find easier. Essentially what you're doing is you're using log x on the horizontal axis instead of x. So that's probably what students will have done in school if they use log graph paper. They'd have said, instead of writing x, I'm going to write log x on the horizontal axis. An alternative is to produce new graph paper, so the horizontal axis is essentially log x, but, and here's the key thing, instead of writing log x, you write the actual values of x on the paper, because then it's easier to work with, because I can do my mapping straight from the xy data instead of first having to get my calculator out and write log x. So in essence, all the log calculations are done by producing the relevant graph paper rather than using a calculator. Now this will be clearer once you see the graph paper next. So here is an example of some log graph paper. Now you'll see the numbers are written. If I write down this is the x-axis, the numbers are written down as the actual values of x. So I've got here 0.1, 1, 10, 100. Okay? So 10 to the minus 1, 0.1, 10 to the 0 is 1, 10 to the 1 is 10, and so on. So the graph paper, when you print it, you put the actual values of x. But the next question is, where have those positions come from? Well, if I take the log of x, okay, which is what we're actually doing when we choose this graph paper, then the log of 0.1 is minus 1 if we do log 10. The log of 1 is 0. The log of 10 is 1. The log of 10 squared is 2. And you can see, in fact, the actual number has come from this power here. So when they put the log scale on, they sort of help you out a bit. Okay, so you can view this as two different ways. Either you put x on a log scale, or you can view it as log x. Now to make this a little bit easier, you'll notice these vertical lines are not equispaced. So you're now looking at these lines saying, what do these lines represent? Well, I happen to know that the first line represents a value of x equals 2, the second line a value of x equals 3, the third line x equals 4, and so on. And if I go to the next decade, the first line will be 20, the third line will be 30, and so on. So you can see the spacing for different values of x is not the same. And you might say, well, how on earth would I know what this spacing should be? So this is how we're going to do it. So you can basically produce some graph paper, log graph paper very easily yourself, should you need to. Let's look at a single decade, 1 to 10, and I've broken it in half. You'll see there's two purple bars, basically split it in half, and there I've got that vertical red line to say it's split in half. So if I put the log here, then obviously this vertical line corresponds, sorry I should use red, this vertical line corresponds to log x equals 0.5. Now if I said to you log x equals 0.5, then you would tell me x is approximately 3. And what do you notice? That this vertical line has pretty much overlaid where we've got the vertical line for 3. Let's now split this next bit again into two equal parts. So you can see the first vertical line corresponds to log x equals 0.75, and the last one obviously to log x equals 1. So if I said to you, if log x equals 0.75, then you tell me that x is approximately 6. I know it's not exact, but we're only doing a rough sketch here. And again, if you look, you will see this vertical line with the red line roughly overlays the line which corresponds to x equals 6. So the key thing is, you could, if you wanted, draw your original log x values and use the values that you know. So you know things like log 10 of 2 equals 0.3, log 10 of 3 is approximately 0.5, and so on, and therefore you can find the positions of these vertical lines and then write your graph paper in terms of the original variable x, which makes it easier to use. Now, what's the interpretation of log graph paper? You notice the key thing here is you get equal weighting or equal spacing on the graph paper for different decades. So you see the space to go from 10 to the minus 1 to 10 is the same as the space to go from 10 to the 0 to 10 to the 1, same as the space to go from 10 to the 1 and 10 to the 2, and so on. And that can be very useful in some scenarios where your data is quite spread out, but you've got equal information content in different decades. So equal distance in a log paper is equivalent to equal scaling. So this is the other thing. If you look at these two double arrows that I've just put on, there's actually something quite interesting about those. Those are the same length. So if you look at what I've done, with the first one, I've said log x has gone from -2 to 1. So you can see here, that's roughly minus 0.2 in terms of log x. And this value here is 1. Okay, so the distance I've moved in the log scale is 1.2. But if I look at the underlying values of x, you'll see there were 0.6 and 10. So in other words, 0.6 equals 10 to the power minus 0.2, and 1 equals, have I got that right? Sorry. 10 equals 10 to the power 1. Okay. Now let's look at the other vertical line. So this one here. And see, in this case, the log values went from 0.5 to 1.7, which is also a change of 1.2. So you can see both those lines have got the same change. The underlying values of x were 3 and 50. Now what do you notice? A change of 0.6 to 10 means you multiply by 16 and 2/3. A change from 3 to 50 means you multiply by 16 and 2/3. So in other words, because the change in the horizontal axis is the same, the implied multiplying factor is the same. And that's a really useful insight that you can apply when using log graph paper. Now, just a quick analogy for you. Anyone who's a musician will be familiar with a keyboard, and what you'll notice is that you get equal spacing for each octave. So you'll see if I put an arrow there, I've gone from one note to the equivalent note an octave higher, and what you notice, you have the same spacing on the keyboard for each octave, which is equivalent to a doubling of the frequency. So why do engineers use logarithms? They simplify multiplication and division, because multiplication and division now become addition and subtraction, which are a lot easier to visualize. Addition and subtraction are just a shift. There's a strong link with the exponential function and the logarithm. Now, because exponentials occur naturally throughout engineering, implicitly therefore, so do logarithms. So, conclusion. We've demonstrated two core skills in the use of logs and exponentials. How do you identify whether there's an exponential underlying some data, and where that data is likely to be noisy? And we've basically said take the log of the data and if it's a straight line, you can see there was indeed an exponential underneath it. And we've looked at the generation and use of logarithmic graph paper.